Good evening, everyone. Last class I have discussed about one-way slab. Today I will discuss about one-way slab having a special criteria where it is in cantilever condition. So we may call it cantilever slab or structure. So cantilever beam we have already discussed in beam section. So here in slab there's some in here we our training. So such a the condition that one end will be standard will be and like here for slab we consider a one we design beam kindly. So the condition can support to the and for a cantilever slab, and if the slab is continuous then we have to consider the to the support and the center to center distance of the support. So this is the condition to be considered for effective span of slab depth. That is from the deflection consideration. And for the 1/2 and criteria in the at the top of the curve. So these are all the points that is to be kept in mind before we start the designing. So let us discuss about one example of the cantilever slab. So there is a cantilever slab of having an overhang of 1.2 meter and it is carrying imposed load on the slab that is 1 kilonewton per meter square, and the life load is considered with a finishing of 800 newton per meter square, and it has been asked to consider M20 grade concrete and F415 steel. So before we begin we have to first take out the total imposed load, that is the total imposed load, that is 1 kilonewton means 1000 newton per meter square plus 800 finishing load newton per meter square. So total imposed load comes as 1800 newton per meter square. FCK is 20 and Fy is 415. Now assuming the depth of around L by 10, we will get the around 120, 150, and effective depth we have considered as 125. That is by subtracting the effective cover and the value of the dia. So dia of the reinforcement. So the effective span will be the overhang length, means the length from the free end to the support, and plus half of the effective depth, that is half of 0.15 to 0.15 meter. So that comes, the effective span is coming 1.26 meter. Okay. Next part is to calculate the design load and factored moment. So we have to first calculate the self weight of the slab. So self weight of the slab, for considering the unit weight of concrete as 25,000 Newton per meter square, 25,000 Newton per meter cube, as 0.15 into 1 meter strip we are considering, and 25,000 Newton per meter cube. So total weight of the slab, depth into the width into the unit weight, we are getting 3750 Newton per meter. Imposed load we are considering for 1 meter strip, so 1800 into 1, 1800 Newton per meter square into 1, so 1800 Newton per meter is the imposed load that is required for calculating the factored moment. Next is your design load. So design load will be the fact, we have to multiply the total load with factor 1.5. So the total load is coming, the self weight plus imposed load, as 5550 Newton per meter. So multiplying it with the factor 1.5, we are getting 8325 Newton per meter as the design load, W. And for factored movement mu, that is WL square by 2 for maximum bending moment at the maximum bending moment for the cantilever condition, that is 8325 into 1.26 square by 2. So from here we will get the factored moment mu, that is 6608 Newton meter, and we have to convert it into a Newton millimeter, and the factored shear force will be the designed load into the effective length that we have got, the overall the imposed load using the self weight and imposed load, we have got the total load, and from there we have got the design load, and from there we will multiply it with the overhang length to get the factored shear force, VU. Next step is to find the minimum effective depth. So for this criteria, we have to find out the value of RU. So for a M20 grade concrete Fe45 steel, we know that the value of X max by D is 0.48, and from here we will find the value of RU using by putting the value of X max by D. So we know that the equation for RU is 0.66 X max by D whole multiplied by 1 minus 0.42 X max by D. So if you multiply, you will get the value of RU, and D required is root over of mu by RUB. So all the values are known, and by equating, you will get the value of D required. So while taking the value of mu, we must take care about the unit. So since here 1 meter strip width is considered, so B turns as 1000, and mu is the value that we have got from the design factored load, factored moment, and d required is coming 49 mm, so that is much less than the effective depth, that is 125 mm. So hence the section is under enforced, so it is okay. Next step is to find the area of the steel. To find the area of the steel, we have to consider the value of mu and equate it with the value 0.87 fy ast into d whole multiplied by 1 minus fy ast by bd fck. So from here only unknown is ast. So from this quadratic equation we have to find the value of ast. So after evaluating you can find it. The ast value is 148 mm square. Now for the standard criteria, we know that this area of the steel that we obtained should have the minimum area of the reinforcement, means it should be 0.12% of the cross sectional area. So we have to take out the minimum cross section, that is the 0.12% of the cross section, that is 0.12 bd by 100. So while taking out we have to make sure that don't commit any mistake that it is not effective depth but it is the overall depth. So 0.12 bd b capital D by 100, so that is coming 180 mm square, so which is more than the area of steel that we have equated from the equation. So since the value that obtained from the equation ast, which is lesser than the minimum required value of 0.12%, so we will consider the maximum area, that is 180 mm square. Now next step is to distribute this bar. So if we use 8 mm bar, then we know the area pi over 4 d square, and from there we have to find out the spacing. So the spacing that is obtained is coming 279 mm. The values, so let's suppose to now we feel, so that 100 it is kind of limit, the maximum it is not crossing the maximum limit, so we can provide 8 mm 270 mm at 8 mm bars at a distance of 270 mm center to center for main steel. We can also provide the same bar in the distribution as a distribution enforcement. The same bar could be provided with the same distance 270 mm center to center in other direction, in transverse direction, that is your distribution enforcement. I hope up to this much everyone has understood. No problem. Next step is to check for the shear. The shear value already obtained, and we have to also calculate the minimum AST provided. So the AST provided is 186.3 meter square, millimeter square, and the nominal shear stress V by BD we can obtain zero. Now next step is the design shear strength of concrete. So for design shear strength of concrete, you have to consider uh, refer to table 19 of IS 456. So from table 19 of IS 456, you have to consider the value of PT, that is 100 AST by BD. For the consecutive value of AST, you have to find out the value of tau C, that is design shear strength of concrete. So 100 here, AST considered is 186.3, D is 1000 and D is 125. So we have obtained the value of PT as 0.15%. So C for the consecutive value of 0.15% from the table, and for the particular grade of concrete here it is 20. So for that the value of tau C is coming as 0.28. So for this we can consider the value of tau C as 0.28 Newton per mm square. Now again for next table, from for to obtain the value of uh, K for the consecutive depth, the overall depth of the slab, that is 150 or less. So for this condition, the value of small k is coming 1.3. Now we have to check, we have to multiply this with the uh, k into tau c factor. So 1.3 into 0.28, that is coming 0.36 Newton per mm square. So this value is coming, much more than the value of tau v. So hence it is fine. So since the minimum shear reinforcement that is provided, the shear criteria is fulfilled with the provided reinforcement. Development length. To check the development length, we have to refer to clause 26.2.1 of IS 456 for permissible bond stress for plain bar and deformed bar. So for consecutive grade of concrete, we have to take out the value of tau BD. So here the, since it is a deformed bar, so here the value of tau BD for M20 grade concrete is 1.92. So the requisite value of development length LD, we know that the formula is 5 into Fy by 4 tau BD. So by providing all the values in the equation, we'll get the development length value. So this is the minimum development length and that we can provide in practical. So next step and the last step is to draw the sectional elevation and provide all the values and show all the values by and label all the values for the particular reinforcement that are provided. So the development here is how generally and show that has been provided and the all and effective length of the slab that is provided with the overall depth. Next step is to check for the deflection. So to take out the deflection, we have obtained the value of f, that is 0.5 into st required by st provided. So fy is 4.5, 0, so it comes as 0.58 into 30, and st provided is 193.5. So ultimately it is coming to 23. So for the consecutive value of pt as 0.15% and fs 223 Newton per mm square, from there we have to take out the corresponding value of kt, that is 2.0. So value of obtain the L by 2, we will L by divided. So here is coming the L by D max is more than L by D. Then all the checks has been done for the with the requisite minimum value with the design with the code. Next is your continuous slab. So from the continuous slab, what we understand, it is a slab that is cast monolithic. The enforcement that in the beam bears with the member. The member are actually out the span with a multiple number of supports that it carries. So the T-beam that are spaced at regular interval of the slab is also called continuous slab over this support. So there are some points that to be remembered for design of this continuous slab. So for this we have to consider the coefficients that are applicable for finding for the given moment and shear force value for any critical section. So in the section, as you can see, L1 and L1 is the corresponding effective length that is considered, that is for a continuous slab. We have considered the center to center distance between the support, and hence it will continue, means L1 will have a effective length, effective span, then L2, then L3 and L4, and hence it will proceed like this. And we have to provide the solution bar, and the curtailment should be provided at certain interval, at certain distance. And we know the criteria that it should be having 50% of the area, overall area, and the curtailment distance should be more than 0.1 of the effective span, and the portion where it is fixed, and for the portion where it is continuous, means at the intermediate point, the value should be more than 0.15 L. So we can say that the slab, when it is continuous, so if it is continuous for over 3 or more spans at least, then which will not differ by more than 15% of the longest span, and loads are mainly uniformly distributed. So this coefficient that are provided for the given method of IS 456 2000 this criteria should be applicable, then only the coefficient is applicable. Now, there is another term called redistribution of moment, and because of this, there is not any permission for any movement that are determined using the moment coefficients. So this movement and in their deflected profile will be certain change in the movement, and that will compound it, and the values will actually change. That is the criteria for movement distribution. So for those conditions, this coefficients will not be applicable, and the moment that are determined will be from the moment coefficients only. The criteria for your continuous slab. Now, if the span of the continuous of the uh, portion of the slab when it is at the corner, and the intermediate span, if there is a difference of more than 15%, then a rigorous analysis of the slab is required using the method like Kani's method. So Kani's method, all of you know, is a method of analysis, and moment distribution method is also a analysis method. So when this factor that the slab, the effective span is having a difference in the span, then the design of the slab becomes complicated because of the requirement of the analysis to be done before we build the design. That's in terms of using the methods of analysis of Kani's method or moment distribution method. So as the moment as the reinforcement detailing as shown in the figure previously, as you have seen, so this is the condition, and criteria for the bending moment and the shear force coefficients for this continuous slabs are given as below, as you can see in the table. For mid span and support moment, dead load is considered, and the end span, then the bending moment coefficient is plus 1 by 12, and for interior span is at support next to the end support. So the support that is next to the end support is minus 1 by 10 by 12. Whereas the live load is plus 1 by 10, and the interior span is plus 1 by 12. Whereas for support moments, the portion where the support is next to the end support is minus 1 by 9, and for interior the bending moment coefficient values for different criteria and different position of the slab. So bending moment coefficient is alpha m into W into L square. So total bending moment will be alpha m into W into L square. So where alpha m is the coefficient as given in table 1, and W is the total design load, and L is the effective span. Now next table is shown with the shear force coefficient. So for loading criteria, design load plus live load, we have three conditions. One is your end support condition, one is your support next to the end support condition, that is also again subdivided into outer face and inner face, and next condition is your interior support, means the support that is neither end nor the nor the support that is next to the end support, means the the interior support have different coefficient of shear force. So for end support is 0.4, for support next to end support outer face 0.6, inner face 0.55, and other interior support is 0.5. And for live load condition, it is 0.45, end support is 0.45, support next to end support, outer phase 0.6, inner phase 0.6, and as well as other interior support is also 0.6. And shear force value is obtained by the equation alpha F into W, where alpha is the quotient as given in the table and W is load. Some exception. So when is built in wall, so for me to provide full because of only part, the negative moment that is shown on carried as WL by 24. So for this special criteria, the shear force coefficient at the end support will be increased by per 0. So let us discuss this by using an example. So it is asked to consider a reinforced concrete slab of a hall measuring 8 meter by 6 meter, and the slab is supported on RCC beam. The support is given width having 250 mm and spread at 4 meter center to center. So this is the condition for continuous slab. So when this center to center term is coming, you have to understand that it is the condition for continuous slab, because this beam is supporting the slab at particular distance. Next is the imposed load. Imposed load criteria is 4 kN per meter square given M20 grade concrete and Fe415 steel. Bearing of the beams is asked to take 200 mm. So let us start. So first we have to take down all the values that are provided. One is your width of the beam of the support for the slab, that is 250 mm. Span of the slab, since center to center value is given, so it will be 4 meter. Superimposed load as given is 4 kN per meter square. So for 1 meter strip it will be 4 kN per meter, and Fe for one and Fy is 415 Newton per mm square, FCK is 20 Newton per mm square as given. Next, the first step is to find the thickness of the slab, means depth. We have to find the effective depth of the slab. So assuming L by D condition, the L by D has nearly about 30. So we will assume that initial depth as 120 mm. So the overall depth, considering as 150 mm, and considering the effective cover as 30 mm. So after this we have to first find the effective span. So given width of the support here is 200 mm. So clear span will be 4 meter minus 0.2 meter. So that is 3.8 meter, because it is center to center distance of the support. Next is we have to consider the width of the support. So considering 1 by 12th of the clear span, that is 3800 by 12, that is 316.5 mm. The support the obtained is given less than 1 by 12th of the clear span. So hence we have to provide effective span as clear distance plus effective depth. So 3800 plus 120 mm will give us the effective span. Now next step is to find the load calculation. Self-weight of the slab. So taking the unit weight as 25 kilonewton per meter cube. So effective weight of the slab will be overall depth into 1 meter strip width of the slab into 25. So that is 3.75 kilonewton per meter square. Next are the imposed load that has to be considered. So here we can consider a finishing load 1 per meter square. Could 4.7 square. So the factored load will be 1.5 multiplied by the total dead load, that is 7.125, and factored imposed load will be 1.5 factor multiplied by 4, that is 6. Now next we have to consider the bending moment and shear force coefficients. So from table 12 and 13 of IS 456 we can obtain the corresponding value of the coefficients. So as shown in this figure, for the slab that is drawn, as you can see, so this and force. So for values of coefficient near the, whereas the shear force for dead is 4. And for intermediate support, that is just next to the end support, it is minus 1 by 10 for dead load, and minus 1.9 minimum, and shear force it is 0.6 for both the conditions, dead load and live load. And again the interior support condition, it should be minus 1 by 12 for dead load and minus 1 by 9 for live load. And similarly for shear force, the coefficient value should be 0.5 and 0.6 respectively. So by this way, and next will be the mirror value of the this value, because it is, if you see the center of symmetry at the midspan, if you see at the third support, so from there both the end will have the similar value. So by this way we can obtain the different values of coefficient for every span, for every support of the continuous slab. Next is to find the corresponding bending moment and shear force value for by using these coefficient values for every slab section. So multiplying all the coefficients using the equation for bending moment and shear force, the maximum moment, as we can see, at support next to the end support is coming minus 21.2 kilonewton meter, whereas the maximum shear force that occurs outer side of the support next to the end support, it is coming 30.87 kilonewton. So both the values are obtained for outer face and inner face of the shear force criteria. Next is the depth check. So for here we know that we have to require the value of RU. So that is already obtained for consecutive value of M20 grade concrete and Fe415 steel. So that is the RU is considering 2.76. We can obtain the required depth, that is root over of mu RUB. So depth required here obtained is 88 mm. So that is less than 120 mm. So hence it is okay and it is under enforced section. Next is we have to find the area of the steel reinforcement. So we have to obtain the value of XU limit, that is 0.48D for the corresponding value of M20 grade concrete. 0.48 into 120 is 57.6. So distance for the balance section MU limit is given by the equation 0.6 is FCK B XU limit whole multiplied by D minus 0.42 XU limit. So from there we have obtained that the MU limit value is more than MU. Now considering singly reinforced section, under reinforced section, from the equation mu 0.87 Fy into AST into D whole multiplied by 1 minus Fy AST by FCK BD, we will obtain the value of corresponding area of steel. Okay, that's all for today. All of you write your name and roll number for today's attendance.